People often ask themselves, is informationism worth the effort to learn about or to contribute to if my goal is to do as much as possible to help with alignment? Many people are unsure about the answer to this question because they aren't clear on how how informationism fits into alignment. Connell and I hope to give you a clear picture of the ways that Vanessa and Diffractor believe IB could help with the alignment problem, as well as the doubts of other alignment researchers about how valuable IB will end up being for alignment. We hope to paint a clear, balanced picture. One of the strategies we're going to try in order to help you understand how IB could help with alignment is to present IB as one part of Vanessa Kosoy's wider research agenda. We hope that situating IB within this wider framework will help you see why Vanessa thinks IB is useful for alignment. So with that goal in mind, let's take a look at Vanessa Kosoy's Learning Theoretic AI Alignment Agenda. If you want to dive deeper, I recommend reading Vanessa's post about her research agenda and Steve Byrnes' critique of Vanessa's agenda. I will draw heavily from both of these sources during this video. There are three core beliefs that motivate Vanessa's research agenda. First, Vanessa believes that the solution to the alignment problem must rest on a rigorous mathematical theory. In physics, we have a theory about how projectile motion works. This theory is mathematical in nature. Projectile motion can be modeled by a set of equations, and we can prove things about the path a projectile will take in a specified scenario. We have a ton of confidence in our ability to predict what will happen in scenarios involving projectile motion. We have a good understanding of projectile motion to the extent that we have a mathematical framework to model projectile motion. Vanessa has a very strong intuition that in order to have any hope of building the kind of AGI that is aligned with human values, we need to find a mathematical theory of what intelligence is and how it works, much like we found a mathematical theory of what projectile motion is and how it works. When theorizing about how to align AGI, Vanessa believes we need a set of equations that we're confident in. We need to be able to make formal mathematical arguments about whether or not a particular algorithm will or will not be aligned with human values. Vanessa doesn't expect our mathematical theory of intelligence to be quite as precise as our mathematical theory of projectile motion, for instance. She envisions making progress by starting off with a very oversimplified model of intelligence that makes lots of assumptions about the environment, the agent, et cetera, lots of assumptions, and then removing assumptions one by one and improving the model until it stands up to reasonable scrutiny and contains only reasonable assumptions.
As you know, there are different approaches which are very different. Like some people are doing empirical research, some people are trying to make interpretability tools. I'm personally interested in the side of creating mathematical theory. It feels to me like the most neglected area because there's a number of groups doing empirical research and a number of groups doing interpretability. But when it comes to theoretical mathematical research, what Paul is doing is also kind of theoretical, but he's not really using a lot of mathematical formulas. There are really not many people. I mean, Miri were kind of leading the effort in that direction, but recently they, kind of pivoted. So I feel that the theoretical mathematical research is something where really missing, and we could use more researchers. So yeah, I think that people who are capable of working the problem from this angle, I think they should be doing that. There are a number of reasons, or like maybe a number of ways to look at it. At like why mathematical rigor is so important. One way to think about it is that, or like one reason is that mathematical theory gives us a vocabulary to talk about the problem, right? Like, for example, if I make an analogy with like thermodynamics and building engines, right? Or like building like machines, then thermodynamics gives us a lot of concepts like energy, entropy, heat transfer, so on and so forth. Without having this vocabulary, even when you're discussing something informal, when you're not actually like making calculations or proofs, even when you're just thinking about the problem, just having those concepts is really important to make your thinking a lot clearer on the topic. And like to have this vocabulary to understand what the correct concepts are, having a mathematical theory is crucial, because like, how would we be able to talk about entropy in thermodynamics if there was no mathematical theory behind it? So this is like one reason. Another reason is that, of course, we want to be able to actually prove that our safety protocols actually work, that they are actually safe. And of course, when I say proof, any proof uses some assumption. Like any model has some assumptions, but this is still an enormous advantage, being able to reduce your confidence, like your claim that this protocol is safe, to some crisp, well-defined assumptions that these are the assumptions that I'm basing it on. And then hopefully those assumptions can be tested empirically, can be maybe inferred from other sciences, and so on and so forth. But it gives you a huge, it gives you an extremely powerful tool to be confident about those things. And when you are aiming at a small target, like I think we are in alignment, then we need to have those powerful tools in order to be able to hit this target. I would say that the third reason why mathematical formalism is important is because if we are relying purely on empirical research, then without an underlying theory, we don't really know how to extrapolate from the research we have. Like we did some experiments, but we got some results, but what does it mean for other architectures? What does it mean for other data sets? What does it mean when we scale our compute? Okay, suppose we observe some trends, but are those trends going to continue indefinitely, or are there some phase transitions? We don't know. We're just like in the dark without like a theory to back all of this up.
Second belief motivating Vanessa's research agenda is that there exists a mathematical theory of intelligence, right? This is not a fool's errand. We don't expect a mathematical theory of Rococo architecture to pop up, right? What would even a mathematical theory of Rococo architecture look like? So why would we expect a mathematical theory of intelligence, right? Why is it reasonable to expect that intelligence would admit of a mathematical theory? Well, Vanessa believes that phenomena that are natural tend to have useful mathematical theories. And intelligence, in her view, informally, intelligence is the ability for an agent to effectively pursue its goals. She believes that intelligence is a natural phenomenon because intelligence has been a very significant force in shaping the natural world. Okay, so Vanessa is also emboldened by the fact that we have already made progress towards a mathematical theory of intelligence, specifically statistical learning theory and computational learning theory, which we'll be looking at shortly.
When I'm talking about a mathematical theory, I'm talking about a mathematical theory of intelligent agents in general. Why do I expect such a theory to exist? That's a good question. And I think there are like multiple lines of reasoning that lead to this conclusion. So one line of reasoning is that in general, I expect simple mathematical theories to exist when we're asking questions that are natural in some sense. So to give an example, if we're asking, what are the fundamental laws of physics governing the universe? That's a pretty natural question, because this question doesn't have any parameters in it. Like there's one universe. Okay, maybe you can argue whether there's one universe, but still, so first approximation, there's one universe and it has certain laws of physics, and that's all. Like, so on the other hand, so you can expect those laws of physics to be simple. On the other hand, if you're asking something like, what's the shape of the continent of Africa? Then it would be ridiculous to expect a simple mathematical formula for this shape, because this is just one continent and one planet out of a zillion of planets out there in the universe that all have all sorts of random shapes. So this is a question which comes with some very, very a lot of complexity hidden in the question of self, like specifying what is Africa out of all possible continents, all possible planets already hides a lot of complexity. So I see it as a kind of law which says the amount of complexity going in should be the amount of complexity going out. If you're asking a very complicated, very specific question, then you should expect a complicated answer, and vice versa. And I think that with intelligence, we are asking a question which is simple or natural. Why? Because in some sense, well, one way to think about it is a theory of intelligence, but another way to think about it is that it's just a theory of metaphysics, right? Like intelligence is an algorithm that is trying to take observations and make inferences about what the world looks like. So this, in some sense, is the most fundamental thing out there. It's more fundamental even than the laws of physics, because the way we derive the laws of physics is by applying some principles of metaphysics, which today have not been formalized. But this is just kind of the flip side of the same coin. You can call it the mathematical theory of intelligent agents, but you can also call it the mathematical theory of metaphysics. So this is kind of the simplicity argument. It's kind of a philosophical argument why we should expect this theory to exist. But another argument why we should expect this theory to exist is just because it already kind of exists. Like we don't have the whole theory, but we are already uncovering parts of this theory. And I feel like it looks like it's there, right? We don't have, the whole ship is not out there, but parts of it are already poking out of the ground from which we're digging it out. And it seems like it's there.
Third belief, motivating Vanessa's research agenda, is that there exists a mathematical theory of human values. I want to be a little bit more precise here. So it's not that Vanessa believes that there is a mathematical theory of human values. More precisely, it's that she believes very strongly that it's possible for us to find a mathematical theory of the values of intelligent agents in general. And then within that larger theory, human values would be a special case. Another question that Agent Foundation's researchers often asks, in addition to the question of what is intelligence really, is, what are human values really? Why should we expect human values to have a mathematical theory, right? In game theory and economics, we can model rational agents who have values as expected utility maximizers. But humans are not perfectly rational, right? So modeling humans as maximizing the expected utility for some utility function usually fails, right? This model of humans usually fails in the real world. But the concept of values is very closely tied to the concept of intelligence because, one uses their intelligence in pursuit of their values. So Vanessa believes that there should be a mathematical theory of imperfect rationality that comes packaged with a well-defined notion of what human values are mathematically, right? For the same reason that intelligence should admit of a mathematical theory in Vanessa's view, because intelligence is a natural phenomenon, since human values are so closely related to intelligence, values are also a natural phenomenon, and therefore Vanessa conjectures that there should be a mathematical theory of human values. Okay. I mentioned just now that Vanessa is heartened by the fact that statistical learning theory and computational learning theory are examples of progress towards a mathematical definition of intelligence. In fact, the name of her entire research agenda, the Learning Theoretic AI Alignment Agenda, is based on these two branches of learning theory. So what is statistical learning theory? Well, in statistical learning theory, we study learning tasks. Maybe I want to build a learning algorithm that can learn how to classify handwritten digits. You feed in a digit 0 through 9, and that's handwritten by a human, and the model is able to look at that digit and classify it as 0 through 9. Maybe I want to build a model that can learn how to solve a maze, a model that can predict when and where the next earthquake will happen, a model that can learn how to make the perfect omelet, whatever. These are learning tasks that we would study under statistical learning theory. What kind of questions do we ask in statistical learning theory? Well, we ask, which learning tasks are solvable or not solvable. If I want a learning model to get to a specific level of accuracy on a learning task, how much training data is necessary? And we study different types of learning tasks in statistical learning theory. Some of the learning tasks fall under the category of supervised learning, some fall under the category of online learning, and some learning tasks fall under the category of reinforcement learning, which can be further broken down into different kinds of reinforcement learning tasks. Vanessa thinks it's pretty obvious that if we are looking for a mathematical theory of intelligence, we should focus on improving our current theory of how reinforcement learning works. The phenomenon of intelligence involves an agent working within an environment in pursuit of its goals, and this is extremely similar to the reinforcement learning, the RL setting. The primary aim of a theory of reinforcement learning is to prove that a given algorithm satisfies certain regret bounds for a given learning task. Regret is just the difference between the reward the learning algorithm actually receives and the utility it would have gotten had it started with a perfect model of the environment. So the upper regret bound, right? There's an upper regret bound and a lower regret bound. The upper regret bound, the maximum regret, is a performance guarantee for the algorithm. In other words, the upper regret bound tells us, at its worst, the algorithm would leave X amount of reward on the table. So Vanessa proposes the following project. First, find a list of desiderata, and desiderata is just Latin for something that is desired, right? Find a list of desiderata, a list of qualities in a program, a list of qualities in a learning algorithm. Find a list of desiderata for which we can prove that if an algorithm satisfied each desideratum on this list, it would be aligned. Okay, so come up with a proof that says, all right, we've got this list of desiderata, and I can prove mathematically that if an algorithm were to satisfy all of these desiderata, it would be aligned with human values. All right. Second, Vanessa proposes that we actually find an RL algorithm for which we can prove that this RL algorithm satisfies the list of desiderata. So I've got Sue here, which is a particular, my name for a particular RL algorithm that satisfies a list of desiderata. Not just any list of desiderata, a list of desiderata for which we can prove that if an algorithm satisfied this list of desiderata, it would be aligned. Okay, all right, you get the picture. Third, what do we do next? Third, we prove that the algorithm, that Sue here, satisfies a performance guarantee. That performance guarantee, remember, performance guarantee is just the upper regret bound, right? Prove that Sue satisfies a performance guarantee. That performance guarantee becomes an alignment guarantee. All right, fourth, we have to do one last little thing. We have to prove that Sue runs in a reasonable time, right? Reasonable time and space complexity. Usually this means just running in polynomial time, right? Okay, this is the realm of computational learning theory. We mentioned statistical learning theory and computational learning theory earlier. Computational learning theory is all about, can we prove that our algorithms are running in a reasonable time and space complexity? Okay, so let's contrast Vanessa's desiderata-based approach with Steve Byrnes' approach, who's another alignment researcher. Steve applies cognitive science to the study of AI alignment, and he takes a particular algorithm that could plausibly scale to AGI on the left-hand side of this diagram here. He takes a particular algorithm that could plausibly scale to AGI. For Steve, that specific algorithm that he studies is specific algorithms in the human brain. And he asks what failure modes could happen if this exact algorithm were to scale all the way up to AGI. And then he tries to fix those problems to yield an aligned AGI. Paul Christiano, who we heard about in a previous video, he's the one who argued for the usefulness of prosaic AGI alignment approaches, follows the same strategy as Steve Byrnes, right? This diagram is essentially encapsulates the prosaic AGI alignment philosophy and strategy, in contrast to more agent foundations approaches and the desiderata-based approach that Vanessa is advocating for. So Paul Christiano wants to take an algorithm X that could plausibly scale to AGI, and he wants to turn that algorithm into a new algorithm, a line of X that is intent aligned. Intent alignment is just a specific type of alignment where the AGI is trying to do what the human wants it to do. It's nearly as useful as the original unaligned algorithm, and it scales as well as the unaligned algorithm. Let's take a look now at some of Steve's criticisms of Vanessa's desiderata first approach to alignment. I definitely recommend reading Steve's article on Vanessa's agenda. You'll get a fuller picture of what Vanessa's research agenda is. So Steve just describes her research agenda very clearly. And you'll also hear some well thought out and well articulated criticisms of Vanessa's agenda. And you'll also be able to see Vanessa respond to those criticisms. Steve's first criticism has to do with what he sees as weak connections between the desiderata-based approach and the actual failure modes for AGI that we are worried about. I'm just going to read straight from Steve's post here. Steve said, a Vanessa-style indirect argument that an algorithm is corrigible might look like this. So corrigibility just means there are several different definitions of corrigibility, but one way to think about corrigibility is that the AGI would allow itself to be turned off if, in fact, that's what the human wanted to do, right? So here's how Steve pictures a Vanessa-style argument for corrigibility might look. Vanessa saying, here's the desideratum. That is the thing that we want the algorithm to do. And if the algorithm does that or something very close to that, then it will be safe. And our regret bound proves that the algorithm will indeed do something very close to that thing. Will the algorithm seize control of its off switch? In other words, will the algorithm be uncorrigible? No, because that would result in bad scores on the objective in violation of our proven regret bound. Bam, we have now solved the corrigibility problem. Steve finds this suspicious. He says, whenever I think about any actual plausibly AGI-capable algorithm, brain-like algorithms, deep neural networks, rational agents, I keep concluding that making it provably corrigible is a really hard problem. Here we have this proposed solution from Vanessa in which, well, I don't know, it feels like corrigibility got magically pulled out of a hat. It's not that I can point to any particular flaw in this argument, it's that it seems too easy. It leaves me suspicious that the hard problem of the corrigibility problem, hard part of the corrigibility problem, has been swept under the rug somehow, that I've been bamboozled. Pay no attention to that man behind the curtain. And here's Vanessa's response to that. Let me give an analogy. In cryptography, we have theorems saying that if such and such mathematical assumptions hold, then a particular protocol is sound. We don't need to list all possible ways an attacker might try to break the protocol. We get safety from any possible attack within the assumptions of the model. Is this too easy, quote unquote? I don't think so. It requires a lot of hard work to get there, and we're still left with assumptions we don't know how to prove, but we do have high confidence in. Similarly, we're going to need a lot of hard work to get safe protocols for AGI. Another one of Steve's critiques is that he expects that in the future, specific components of an algorithm will correspond to making the algorithm avoid specific failure modes. So for instance, here is a future proposed algorithm for aligned AGI of the type that Steve believes we will get, right? We've got some code, and then, oh, we've got a module in our algorithm that's specifically created in order to defend against deceptive mesa optimizers, for instance, a specific failure mode. We've got some more code, and then we've got a module that defends against incorrigibility, right? And then Steve says, well, then the proof of whether or not this algorithm is safe would need to make specific references to those parts of the algorithm, right? Instead of ruling out a failure mode indirectly, as Vanessa proposes. So there are some criticisms of Vanessa's desiderata-based approach. There are more criticisms in Steve's article, which I'd recommend that you go read, and more back and forth between Steve and Vanessa in that article. Connell and I aren't going to take a position on this in this video series. We hope that you consider the arguments for yourself, form your own view. So let's summarize what we've looked at so far. Vanessa is hunting for a mathematical theory of intelligence. The way that she's hunting for this theory is informed by past work in statistical learning theory and computational learning theory. Vanessa believes we need to find a list of desiderata and prove that if an RL algorithm were to satisfy these desiderata, it would be aligned. Then we need to actually come up with an RL algorithm for which we can prove that it meets all of these desiderata and that has reasonable time and space complexity. We also need to prove that it satisfies specific regret bounds, the upper bound being a performance guarantee, which is actually an alignment guarantee because we proved the algorithm satisfied appropriate desiderata. Okay. Do you remember at the start of the video when I said that one of the modes Vanessa operates in is to come up with a proposed solution to a problem that makes a ton of assumptions and then start removing assumptions one by one and patching holes until the solution only relies on a few very reasonable sounding assumptions? Do you remember that? Well, ICSI is one example of a mathematical theory of intelligence that makes a lot of assumptions. One big part of Vanessa's agenda is patching the flaws in ICSI. ICSI has three major flaws. First, nobody can prove that ICSI satisfies any regret bounds because ICSI is unable to avoid what Vanessa calls traps. Roughly, a trap is an action that causes irreversible harm. So a big part of Vanessa's research agenda is figuring out how to construct learning algorithms that avoid traps. To be more precise, there are specific scenarios in which ICSI would be able to avoid traps if it just gets lucky. So it's not like ICSI will always fall into a trap, no matter what the environment is. The real problem is that it's impossible to prove that an ICSI agent will avoid traps unless we make more assumptions. And even if we assume that ICSI will avoid traps, the regret bound it satisfies in that case is very, very weak for reasons that are outside of the scope of this video. ICSI's second major flaw is that the decision theory it uses is something closely related to causal decision theory, which means that it will fail in what are called Newcomb-like scenarios. We'll be going into more detail about what a Newcomb-like scenario is in a future video. Real quickly, I want to point out that in Vanessa's words, quote, problem number 2 is actually a special case of problem number 3 because Newcombian scenarios are always non-realizable, end quote. Now, the third major flaw of ICSI is that it performs horribly in non-realizable settings. What is non-realizability? It's the hole in reinforcement learning that Infra-Bayesianism attempts to patch. I should say it's the hole in reinforcement learning theory that Infra-Bayesianism attempts to patch. To introduce the problem of non-realizability, let's have story time again. This time I'm going to read through part of Abram Demski and Scott Garrabrant's, both of these guys work at MIRI. I'm going to read through their illustrated guide to embedded agency, which we will see is closely related to non-realizability. Before I get into the embedded agency story, I want to mention that in addition to the 3 flaws that we've talked about so far, the flaws in ICSI, Vanessa sees at least 2 additional major flaws in ICSI. So there are a lot of flaws in ICSI. Both of the 2 flaws we're going to talk about right now are patched up by Infra-Bayesian physicalism, which Connell's going to talk about a few videos from now. So this little mini discussion right here can serve as a little preview for the Infra-Bayesian physicalism video. The first additional flaw in ICSI is that the utility function of an ICSI agent can only depend on its direct observation. So in other words, an ICSI agent can't be rewarded or penalized based on things that happen in the environment that aren't observed by the agent. And this leads to some problems that Connell will get into a little bit more in future videos. Now, the second additional flaw in ICSI has to do with the Solomon-Off prior that Connell talked about earlier. Using this prior leads to the agent being penalized for using what are called bridge rules. Now, don't worry about what bridge rules are for now. Connell's going to discuss them at length in his video on Infra-Bayesian physicalism. All right, embedded agency. This is Alexi. Alexi is playing a video game. Alexi interacts with the environment via well-defined input-output channels. This means that Alexi has a clearly defined functional relationship with the environment, defining action consequences. Alexi can hold the entire environment in mind. Alexi may need to learn what the environment is like, but in doing so, can represent every detail. Alexi thinks about manipulating and controlling the environment, but not himself. He doesn't have the opportunity or risk of arbitrary self-modification because the environment can't really touch him. He can't really die either. He only has to worry about restarts. Alexi may think like a reductive scientist about the world, breaking it into parts, but the concept of agent is non-reductive. Alexi is an indivisible atom which produces actions. This is Emmy. Emmy is playing real life. Emmy is part of the universe, not sitting outside, so it is hard for her to imagine taking different actions. Alexi can poke the universe and see what happens. Emmy is the universe poking itself. Emmy can't hold the entire world in her head. Any model she uses will be very partial and approximate. Emmy can reflect and self-improve. Emmy thinks about how to win, where Alexi only thinks about how to win. Emmy is made of parts, just like everything else. She isn't really a unitary entity. She is just a bunch of stuff. Somehow we get an agent out of non-agentic pieces. This is Marcus Hutter. Marcus Hutter's ICSI model tells us all about the kind of thinking Alexi needs to do to be good at winning video games. The ICSI model sets up a somewhat symmetric relationship between the agent and environment. The agent produces a sequence of actions, which are a function of previous observations and rewards, while the environment produces observations and rewards in a way which is a function of the previous actions. ICSI doesn't know which environment it is interacting with, so it uses a probability distribution on all computable environments. Its task is to learn about its environment through observation and plan to get as much reward as possible, taking into account its uncertainty to hedge its bets. Agent models like ICSI are dualistic. The agent exists outside of the environment with only set interactions between agent stuff and environment stuff. They require the agent to be larger than the environment and don't tend to model self-referential reasoning because the agent is made of different stuff than what the agent reasons about. These dualistic assumptions are not unique to ICSI. They are very common among models of rational agency. We would like to understand agents like Emmy, as well as we currently understand agents like Alexei. ICSI serves as an illustration of what this high level of understanding looks like. However, agents in the real world are forced to break important assumptions of the ICSI model. Agents like Emmy are embedded in their environments. Embedded agents break the dualistic assumptions. They are not given well-defined input-output channels. They are smaller than the environment. They are able to reason about themselves and self-approve, and they are made of parts like the environment. Okay, so after all that, what is non-realizability? Well, in the realizable setting, among all the hypotheses, again, a hypothesis in the context of Bayesianism is just a guess about what the environment looks like. Among all the hypotheses the agent is considering, at least some probability is assigned to the true configuration of the environment in a realizable setting. In other words, there is a grain of truth in the prior. In the non-realizable setting, there is no grain of truth in the prior. Almost all of the current theoretical RL research assumes that the RL agent is in a realizable setting. In these settings, Bayesian reasoning provably converges to the correct hypothesis about the environment. Okay. The agent eventually discovers, the Bayesian agent in a realizable setting, eventually discovers the correct hypothesis. In the non-realizable setting, unless you make some very restrictive assumptions, like ergodicity of the environment, for instance, there are no guarantees about what sorts of behavior a Bayesian RL agent will converge to.
So the distinction between realizable and non-realizable, it comes from statistical learning theory. And in statistical learning theory, we are talking about having some phenomenon which we are trying to learn, trying to model. And there is some class of hypotheses which we're using to describe this phenomenon. So our learning algorithm is taking in data and outputting some hypothesis from some class. And the realizable setting is when there is a particular hypothesis in the class, which is an exact description of the physical phenomenon. The non-realizable setting is everything else when we don't have this exact description.
So is non-realizability a reasonable assumption to make? Not if we're talking about embedded agents. Embedded agents are unable to represent the entire environment in their hypothesis space because the environment contains them, and we get an infinite loop self-referential situation.
In realistic problems, you should always expect things to be non-realizable because the world is very complex. So if you're dealing with an actual physical phenomenon rather than some toy model or just some simple computer simulation or something like that, then because of the complexity, the computational complexity of the physical world, you can never expect that any of your hypotheses will be an exact description. And in statistical learning theory, there's a lot of theory of like what happens in the realizable setting, what happens in the non-realizable setting, but one missing piece there is that for reinforcement learning, we only have good theory, or we only had good theory in the realizable case. And of course, AXI is basically a special case of reinforcement learning, basically reinforcement learning with some specific prior. So what basically it means that if you're just thinking, for example, you can say, oh, I'll just solve everything using Bayesianism. But when you're doing Bayesianism, an interesting thing happens is when you're in the realizable case, so the environment is actually inside your prior, there are theorems which show that you're guaranteed to converge to the correct hypothesis. But when you're in the non-realizable thing, then in general, nothing can be guaranteed. So sometimes you can guarantee something if you make some ergodicity assumptions, but those are also some very strong assumptions that you cannot, that you don't have in general.
So how important, for the purposes of alignment, how central do you see the non-realizability problem? Like how central of a roadblock is non-realizability to making progress towards a mathematical theory of intelligence that we can use for alignment? Like is non-realizability one of the central roadblocks, or is it more peripheral? Where would you place it?
Well, it's certainly one of the roadblocks, and I think a pretty central one, because non-realizability, it's connected to a lot of other things. Like when you're thinking, for example, of systems that are self-improving, then you immediately run into non-realizability, because like you have this paradox that the system cannot have a perfect model of itself. When you're thinking about multiple agents interacting with each other, you run into non-realizability, because it's not possible that each agent can simulate the other agent. You also get some kind of paradoxical loop. When you're thinking of Newcombian paradoxes, then of course you also get non-realizability, because this omega in the Newcombian paradox is non-realizable. When you're thinking of embedded agency, you have non-realizability, because if the agent is part of the physical universe, then the physical universe is bigger than the agent, so it cannot possibly fit into the agent's hypothesis. But so this is kind of something that's popping all over the place, and if you don't know what to do about it, then there's like a whole range of questions that you can't even begin to answer.
So first of all, this is all my understanding. Like I like have engaged with this somewhat, but like I haven't gone super deep into every single piece. So like take it all with lots of salt. So when Vanessa first started working on Infra-Bayesianism, the main motivation, as I understand it, was dealing with things like the grain of truth problem, things like traps. Now, at the time, Vanessa was arguing that these were like particularly central problems to alignment. I think that's basically just wrong. Like traps and grain of truth, like these are things you have to deal with at some point along the way, but I don't think they're particularly central to the alignment problem. And I think the methods of Infra-Bayesianism were sort of optimized for those problems, and like aren't particularly useful for the more central problems of alignment. Now, since then, Vanessa's sort of shifted to working on other things, which I think are potentially more central. So for instance, her work with the bridge law.
Here, John, when he says the bridge law, he's talking about a particular concept that comes up in information physicalism, which we'll see in the very next video.
Was like getting at a much more central piece of the puzzle. And that was formulated in terms of Infra-Bayesianism, but I think it didn't really need to be. Like the sort of core ideas that were going on there were things which you probably could have formulated just fine in an ordinary Bayesian framework. Miri was originally focusing on problems of self-reference, which inherently like gets you to problems of non-realizability and traps, because like you end up with environments where something may be diagonalizing against you. You end up with environments where like you can't model the whole thing because you're in it, and you can't predict your own actions in real time, that sort of thing, right? So that inherently forces you to deal with something like non-realizability, and the reason that people were focusing on those particular problems was just because those were like relatively legible problems. They were problems which like we had some idea how to talk about mathematically already, and they were problems which like were obviously hard, right? So they were legible, they were hard. This just seemed like a sort of good place to make progress before we had figured out like, or well, we still haven't figured out, I should say. We still haven't figured out like how to talk about a lot of the other problems mathematically.
Got it. So if non-realizability and traps and grain of truth and that kind of stuff, on your view, are not central to the alignment problem, what concepts do you think are central?
Yeah, so the things that I think of as very central are things like abstraction, for instance. At a higher level, things like what are the type signatures of human values, or more generally, the type signatures of like values in systems which will be produced by selection pressures. So like what sorts of values do humans have? What sorts of values is an AI likely to end up with? What are the inputs to those? What are the outputs to those? And similarly, like what sorts of optimization processes naturally end up being produced by selection pressures, like what sorts of reasoning processes do humans likely have? What sorts of reasoning processes will AIs likely end up with? What sorts of data structures do we likely use for representing the world? All that sort of stuff.
Got it. Got it. Is there any part of Infra-Bayesianism that you are fairly excited about? Or do you mostly think it's kind of headed in a direction that's not too fruitful?
So Infra-Bayesianism itself, I think, is like not particularly set. I do think it's a useful tool. Like it's one of those things where at some point we're going to need to solve this particular sort of problem, and Infra-Bayesianism is like plausibly the right tool for that. But at the same time, it's a thing where like I'd expect that mostly we can work out sort of the core problems in whatever framework happens to be convenient. Like if you just want to use plain old Bayesian reasoning, you can probably use that for most of these problems. And then later on, we can port it over to Infra-Bayesianism if we need to.
How confident are you that Infra-Bayesianism will end up being a significant factor in helping us solve alignment?
Yeah, that's an interesting question. Like, I feel that on my inside view, I am relatively confident. Like on my inside view, I feel fairly confident, but I also feel that you know, the kind of beliefs, all things considered, should not put too high weight on this inside view. So I don't know if I want to really put a number on it. I feel like there's a considerable probability that Infra-Bayesianism is going to be crucial. There is also a probability that we'll discover that somehow this line of reasoning was a dead end and that there's something else. So I don't think that there's a negligible probability of either thing. But overall, I'm pretty optimistic about Infra-Bayesianism being a useful ingredient, and kind of definitely pessimistic about solving the alignment without solving the problems that Infra-Bayesianism is trying to solve. Quite pessimistic about that. And, I'm kind of inclined to think that Infra-Bayesianism is the correct solution, but I can't say that I know this with 100% certainty.
All right, so we've seen all three of the major problems with ICSI. One of the major branches of Vanessa's research agenda is to come up with what she calls a universal theory of reinforcement learning that patches the holes in ICSI. One of those patches is Infra-Bayesianism. There are other pieces to Vanessa's research agenda beyond coming up with a universal theory of RL, but I'll let you read about those in Vanessa's description of her agenda. In summary, Vanessa sees Infra-Bayesianism as one piece of the puzzle for aligning HEI. She believes that Infra-Bayesianism could be the key piece of the puzzle, but it's just one piece of the puzzle in a wider research agenda. Many people have trouble seeing how Infra-Bayesianism could help with alignment. I hope that seeing how IB is embedded in a larger, comprehensive research agenda clarifies how Vanessa expects IB to be useful for alignment. Let's look at Infra-Bayesianism in more detail right now.